Electrodynamics. I'm going to go through all the steps to make this. This is a contour plot plus an electric field plot for an electric dipole. And once you learn how to do this, I mean, because I like to use VPython, but we're gonna have to use a mixture of both Python and VPython. But this does make pretty plots, right? It is pretty. We can do something like this in web VPython, but I'm going to show you all the steps. And I'm not a Python expert. I don't know if you know that. I'm not a Python expert. Let's just get to it. So we're going to make this from scratch. But I need to start off with how do we calculate the electric field? How do we calculate the electric potential due to a dipole? And if you can do it for a dipole, you can do it for a tripole. You can do it for a quadpole. You can do it for any number of charges. It's all the same, right? Okay. With that, let's look at our dipole. So imagine that we have a dipole. I'm going to use this dipole here, a positive Q, a negative Q on the y-axis. How do I calculate the electric field? How do I calculate the electric potential? So let's start off with the electric field first. So imagine I have some location right here. Let's just call that, I like to call it RO, the observation location. Well, I need to find the vector from here to there. I need to find the vector from here to there. So let's go ahead and call this a vector. I'm going to call RQ1 as the vector 0, d over 2, 0. So this is a separation distance of d. And then RQ2 would be 0, negative d over 2, 0. Now I want to find, let's just call this R1, and let's call this R2. So the vector R1 is going to be RO minus RQ1, right? It's going to be the difference between this vector and that vector will tell me R1. Same thing for R2. R2 is RO minus RQ2. And you can use whatever names you want. Now, here's the trick, right? I like to use vectors. And vectors are great in web VPython, but contour plotting doesn't exist in web VPython. That's where I need to combine the two. So I'm going to show you some stuff here that you may not be able to do easily on your own without installing things, but I'll talk to that later. Once I have these, it's pretty easy to calculate the electric field. It's just the sum of the electric field due to these 2 points. So I'm just going to write it as one big expression. I'm calling k 1 over 4 pi epsilon naught, just to make things easier. So I'm using k as 1, q as 1, d as 0.01, because it doesn't really matter. So this is going to be k times q1, the value right there, q1. I'm going to leave it as q1 because you could have it as some other value. You don't have to have a dipole. This works for anything. And then normally we would divide by the magnitude of r1 squared, but then you have to multiply by the unit vector. So you could do this, r1 hat over r1 squared. So you got to find the magnitude. I don't like to do that because that's just an extra step. So instead, I'm going to write this as r1 vector, but then I'm going to need to divide by r1 cubed. And then plus k q2 r2 vector over r2 cubed. And those are magnitudes. And that's it. Now I have the electric field for any particular location. Now we're going to have to do something about that in just a second. What if I want to find the electric potential? It's the same thing, right? V is going to be k q1 over r1 plus k q2 over r2. So I'm not doing any approximation. I'm not doing a dipole approximation. I'm just straight out calculating the electric field, straight out calculating the electric potential. If you want to do a dipole approximation, you can do that differently, but this will give us the map that we want. Okay, that's it. I just need to do this for a whole bunch of points. Now for the tricks. Okay, I got my little self tangled up here. Okay, now I'm untangled. Let's switch over to Python. Okay, switching to Python. We don't need that anymore. Okay, so this is Jupyter Notebooks. You can do a lot of stuff, and I'll give you some ideas about how to do this if you just want to use it on your iPad or something and use Google Colab. So that's built in. It's online. You don't have to install anything. However, if you do want to do it this way, and you want to combine VPython and Python, then you're going to need to install Jupyter Notebooks. I would say go to Anaconda. I'll put a link to that down below, and then it installs everything. But then you're going to also have to go to VPython and install that, and that's where the trouble is. So here in Jupyter Notebooks, I have imported already NumPy and matplotlib to do plotting. And so the other thing I'm going to need is to import vectors, right? And not just vectors. I need vectors, I need the magnitude, I need the unit vector. So I'm going to import those from VPython, which I've already installed. So I'm going to go down here and say from VPython, if you don't have this, it's not going to work, import the following functions: vector, mag, norm. And then I'm going to run that cell just to make sure it works. But now I can write things like, I don't have to, I can say r equals vector 1, 2, 3, and then I can say print r, the norm, which is the unit vector, norm r, and let's see, and then it works. So that's kind of cool and very useful. You don't have to do this. You can do this in the just by brute forcing, calling things x and y's and things like that. Okay, so let's go ahead and put in some values. I'm going to say, like I said, let's say q is 1, d is 0.01, k is 1. Now, the other thing I need to determine the, what do I need to determine? Oh, where my charges are. So I'm going to write those as vectors. RQ1 is going to be equal to vector 0, d over 2, 0. RQ2, Q2 is vector 0, negative d over 2, 0. Now I need the charges. So let's call this just Q1 is Q, Q2 is negative 2, Q. I'm going to need one other thing, but let's just go ahead and define our a function to calculate the electric field and a function to calculate the electric potential. So I'm going to call this def EC for the electric field calculated, and I'm going to give it a vector. So I'm going to call that vector ROT. So and I'm going to use these global variables of RQ1, RQ2, Q1, and Q2. I'm going to globalize those. I'm not going to import those into the function, which maybe that's not the best thing to do. I know. I do things the bad way. I'm a bad person. Okay, but I can calculate this. I'm going to first calculate that vector R1. It's going to be ROT, the observation location I passed it, minus RQ1, and then R2 is going to be ROT minus RQ2. Now I can calculate the electric field. I'm going to call it temporary electric field. It's K times Q1 times R1 divided by mag R1 cubed plus, because I'm including the Q2 in the sign, so I don't want to put minus right here. K times Q2 times R2 divided by mag R2 cubed. And then I'm going to return that value. Return ET. Okay, let's just see if it works. I'm going to print, let's pick a location. RO is the vector 3 times D, 2 times D, 0. And then I'm going to print EC RO. And there, it worked. I mean, I guess it worked. I don't know the actual value. Okay, so we have a function for that. Now let's make a function. It returns a vector value, which is important later. Now let's make a function for the electric potential. So def VC, it's going to be ROT. I'm going to give it I have to give it a vector location. Yes, the electric potential is scalar, but I need to give it a vector. So let's just do the same thing. I'm going to copy these because why would I retype them if I can just copy them? And I didn't even copy them. And then that's going to dedent. Okay, so I need those two again. And now I can say VT is just going to be K times Q1 divided by mag R1 plus K times Q2 divided by mag R2. And then I'm going to return that. Okay. And then let's just test. Oh, I got rid of my observation location. I think it's going to work. Let's not worry about that. Okay, we should save this. Electric field potential, I've misspelled that wrong. Potential plot. Okay, next, we need to make a space over which to calculate our values, right? We need to think about x and y, a grid of x and y points. So to do that, we're going to have to, now we're going to use, we didn't use any real Python yet. You can do everything here in WebVPython, but the grid stuff is really nice in in Python, and as well as things like arrays. So what I'm going to do is to make a list of x values. So x is going to be np.linspace. I'll show you what this does. Linspace, and I want to go up here. Let's say n is equal to 10. So and I want to pick a, let's say L is equal to 4 times D. I don't know. So I want to think about how big of a space I want that I'm going to make my map for. So it's going to be L by L, or it's going to be 2L by 2L. So let's make this, we can change that. So linspace makes an array of values from start to finish and how many numbers I want. So I want to go from -L to L in, and let's print that out, and I'll show you what it looks like. So this is 10 values from -L, which is 0.02, to L, and you'll notice it doesn't really space out really fine, which is fine if you want. However, the trick is to, if you make this it goes from -0.02 to 0.02, and so that's 10 things. But if I want 11 things, if I just add this n plus 1 and I print it, you get something much nicer. So you don't have to do that, but I like to do that. Okay. So then I'm going to do the same thing for y. So I want an x by y grid, right? So x is np. So np is from the numpy module, and linspace makes it array. So you have to do that. You can make an array in different ways, but linspace is the easiest. From -L to L n plus 1. Now I have an x array and a y array, and I want to combine them together to make an xy array, right? Because I want to go all the combinations of x and y points, and I need to do it twice. So I'm going to say this, I'm going to use capital X for my x values, capital Y for my y values, and we're going to use this thing called mesh grid, mp.meshgrid, mesh grid, and then I just get it x and y. And then I'm going to print that out. I'm going to print out x just so you can see what it looks like. So now I have all the values of x and y, all the combinations of x and y for my x's, and then I have all the combinations of x and y's for my y's too. So this is what you need to make a contour plot and a quiver plot. We're going to do both of those. Okay, so we're rolling right along here. So now I have a list of x and y values. We can make it bigger later, but let's just start off what we have. Let's go ahead and make a contour plot first. So I want to calculate the electric potential for all space. And one of the ways to do this, and this is a little trick I have the x values, and it's a grid. I have the y values, it's a grid. I want to start off with v values and look at the x values and y values to calculate it. So I'm going to do this. I'm going to say v is equal to 0 times x. And let's just print that. I'm going to show you what it looks like. It's not the best way to do it, I know. And so now I have all zeros. And so now I can go through and change these, right? But I have to have those so I can change them. So how do you go through all of these values? Here's what I'm going to do. For I in range n plus 1, because I know how big it is. And then I want to do a double loop for j in range n plus 1. And let's just print. I'm going to print the v values, which is stupid. So I'm going to print vij. That's all it's going to do. And it's just going to give me all the values of, that's going through all the values of v. But now I can change those values, right? If I can print those values, I can change those values. So let's say vij, this is really nice to be able to do this double indices right there. Is this going to be equal to, I need to do this first. RO, my observation location, is going to be equal to a vector, and I want to give it my x values, x, I, j, y values, y, I, j, 0. So as I go through, not 0. As I go through my list, I have x and y values. I'm going to put them into a vector called RO. Now I can use that vector to calculate the electric potential. So this is just going to be VC of RO. That's it. And after we've done that, let's print out print V, just so you can see what it looks like. So now I have values there, right? It's kind of cool. We're done. We just need to plot it. So let's do a contour plot. So this is going to be plt.contour. I always spell this wrong. I need to give it my x, y, and v values. So x, capital Y, capital V, and let's just show that. So I'm going to put plt.show, and let's run it. And there we go. And you're like, but wait, that doesn't look like what we had before. So we do have a problem here. We have a problem in that it wants to make, first of all, I can make as many levels as I want. So I could change this to, let's do 15 levels. Levels, this is how many lines it makes. Levels equals 15. So now I have more lines, but it still doesn't look great. It's a lot of empty space. Because as I get really close to those points, my potential goes to really, really high to infinity. And I'm going to cheat, right? I'm going to cut off the max. And there's more than one way to do this, but I like to do it my way. So let's go up here and say Vmax is equal to 30. I'm just picking a value. We can change that later. So once I go through this, I calculate Vi. Now I can say if Vij, the one I just calculated, is greater than Vmax, then I'm just going to set it equal to Vmax. I'm thinking about like Close Encounters of the Third Kind. The guy was building the mountain and then he just chopped off the top. That's what we're doing. We're chopping off the top. So if that's true, then Vij is just going to be equal to Vmax. And then we want to do the same thing for the negative. If Vij is less than negative Vmax, then Vij is equal to negative Vmax. Nope, max. Let's run it and see what happens. Doesn't that look nicer? Now maybe my Vmax is too high. Well, I don't know, right? So let's say, or too low. Let's make this 100. Let's just try. You play around with it, right? Okay, it looks a little bit better. But still, we can play around with this and we'll make it better very shortly. But there's our contour plot, our equal potential plot. And it is kind of jagged because it's only 10 by 10, right? I can make that 100 by 100 if I want to. Let's make it 100 by 100. So I just have to go up here and change n to 100 and run that. And now you get something that looks pretty nice. Okay. Now I'm not going to want to do that. Let's put it back at 20 because my electric fields are there are going to be too many electric fields. And there's a way to fix that, and I'll tell you, but I'm not going to do it. Okay, that's pretty good. Now I want to go back and calculate the electric fields and plot the electric fields everywhere. So I don't really have that much to do. Up here, I need to calculate, in order to do a vector plot, we need to do what's called a quiver plot. You need to give it x, y, ex, and ey values. Okay. So up here, I'm going to go through all my values. First of all, I'm going to go ahead and create ex is 0 times x. Ey is 0 times y. So now I have values for them. And I could have done, they're both the same, ex and ey. So over here, when I calculate v, I'm just going to go down here. I'm going to calculate, I'm going to use the same observation location. I'm going to calculate ex. I'm going to calculate ey. So ex is going to be exij. Is going to be equal to ec, and I'm going to give it the observation location. Now, that gives me a vector back, right? But I want a scalar value for my list. So I'll only want the x component here. So this is just going to be dot x. In VPython, if you add a dot x, it just gives you the x component. And then eyij is going to be ecro.y. And I'm pretty much done, right? I went through and did everything. So all I'm going to do down here is to add my quiver, plt.quiver. I need to give it my x values, my y values, my ex values, my ey values, and let's run it. Okay, good. We can fix this a little bit. I'm going to fix it a little bit because one of the things is that this is good. There's two things you could do. I could limit the maximum size of the arrow or change the size of the arrow. But what if I want to have all of the arrows the same size? That's the way it looks the coolest. You just have the direction of the field and you don't have the magnitude of the vectors in there. Well, we can fix it pretty easily. Let's just go back up to our function right here where we calculate the electric field. Instead of returning the electric field ET, I'm going to return norm ET. So I'm going to give the unit vector in the direction of ET instead of the total electric field. So they'll all have a value of 1. So it will look a little bit different now. And that looks pretty cool. Doesn't that look better? You can kind of see the shape of the field. I'm pretty happy with that. Pretty happy. Now, I have to do one more thing. Okay, what did I say? I said there was another way to fix this. I said something. Okay, one thing, if you want to have more smoother contour lines, but not too many electric field lines, you can actually make 2 different XY values. I can make an XY up here. I can make an X2, Y2 that has a different number of points in it. And that way my quiver plot and my contour plot have different numbers, but they're plotted on top of each other. That's just nice. Don't you think that's nice? Okay. Now let's do the stuff that I'm terrible at, but you want to do. You're like, hey, make a 3D surface plot. Well, let's do that. Okay, so up here I need to import some other stuff, and you can put it down. You can put it wherever you want. I'll put it up here. From matplotlib, I have no idea what I'm doing here. Import CM. I don't even know. That's like I don't even know what that is. Oops. And then I want to, from matplotlib.ticker, don't know what that is, import linear locator. Okay, so I've imported those things. Now down here, let's start a new cell. What I need to do, I'm looking at my notes here. I'm going to make this thing. I need to make a figure and an axis. So fig and ax is going to be equal to PLT from the matplotlib subplots. Subplot KW, don't know what that means, equals projection, don't know why, colon, is type of 3D, I guess. I really don't know. It's just magic words, right? That's fine. And then surf equals ax.plot surface. X, now here's where I make the plot. X, Y, V, CMap equals CM dot cool warm. I think this is just a color palette that we're using. Line width equals 0. And then let's just leave that off. There's some other things in there. And then PLT dot show. Let's see if this works. There you go. That's what you wanted, right? Now, you can't rotate this around. It's just a picture, okay? But it does look pretty cool, right? That's what you probably wanted. You can change the angle. There's a way you can do the viewing angle. But you can see this is like what you think. There's my negative dipole. There's my positive charge. And that's kind of cool. So there you go. Now, one of the things that I said, you can do this for 2 charges. You can do this for many charges. What if you had a water molecule with a dipole, right? So you have a negative oxygen and 2 positive hydrogens, and then you could plot that. I'll probably do that as a vector field plot in WebVPython if I do that. But there you go. And this is stuff that I forget how to do. So if you find this useful, that's great. But I find this useful because I'm going to come back to this next year when I'm teaching this class. I'm like, how did I do that? I don't remember. I'm going to watch this video. So hello, future Rhett. It's me, past Rhett. Just want to say hi. Hope things are going well, and I'll talk to you later.